For our third basic Morse circle illustration, we're going to take a look at another classic case of, in this case, pure torsion, right? So what I have in my hands here is a torsion specimen. It used to fit together like that, and then it was put in the device and it was twisted until it came apart. And you see that helical surface that's there. That's a very interesting failure surface. We have another torsion bar that was twisted until it ruptured, and note that that failure surface is dramatically different. So we're going to, by the time we're done with this, this example, we will have a little insight to maybe what's going on with those two materials, right? So here we go again. Here's our bar in pure torsion. We learned in a previous block how then to model the shear stress as a function of the applied torque, how far away we are from the center of the bar, the cross section, and of course the polar moment inertia of the cross section. So that's how we get those numerical values, right? So here's our state of stress that we've got for this particular one, and now let's draw a Morse circle that goes with that. Again, first step, always draw your axes. The horizontal is your normal axis, and your vertical one is your shear axis. We'll go to the right with tension, to the left with compression. Shear stresses that are counterclockwise are down below, and then shear stresses that are clockwise are up above. Now, you may notice this time I drew a set of axes that are basically the same length. I looked ahead to something. Notice on this one, there's no normal stresses plotted, and the shear stresses are all equal. That sort of hints and suggests that maybe we're going to end up something that's sort of centered in this whole system, right? Remember that after we get the axes done, next thing is to get 2 points that are orthogonal planes. So point A on this X plane and point B on the other plane. And notice that this one will have no normal stress, and it will have tau acting in a way that would want to rotate that block in a clockwise fashion. Right, so over here, A, right, 0 normal, clockwise, boom, there's your point A, and that magnitude would be tau. Right, over here at B, well, again, no normal stress, and we've got then a shear stress that wants to go the other way, so that would be tau in a counterclockwise fashion. And so same amount, boom, there it goes here. And there's your point B, again, at a value of tau. Notice these two always have to be on opposite sides, because the shear stresses here are on those 90-degree planes are always in opposite directions. That means Morse circle is always centered on the horizontal axis. And this time, Morse circle is going to be centered right on the origin, right? Because the origin of the whole coordinate system is also the origin of the circle. It's which will tell us that the radius is the magnitude of tau. So I can get in these other points, and sometimes it's even handy to get some intermediate ones so that you can draw your arc. Get your circle template out to do this. Right? But if you just want to sketch out a possible answer, this is how you go about doing that. Ugh. Right? Don't like that one very well either. So while you're catching up to me, I'm going to improve my, slightly improve. So that's the basic Morse circle for this situation. Note, it is centered right here. Note that the maximum normal stresses, otherwise known as the principal stresses, will also be equal to tau, right? And on the other side, also equal to tau. One's compression, one's in tension. That's really important, right? We got those maximum shear stresses on the top and bottom. So notice that shear-wise, we have our maximum on the cross-section itself. A represents that slice through the body, and then also there's one at the horizontal layer. Pretty interesting there. But the maximum tension is happening on Morse circle at 90 degrees from the various maximums. That means in real life at 45 degrees from those planes. So So let's go back to our specimen. This one is steel, and it is a ductile steel, kind of, or is it? Ductile or brittle? I mean, you look at that surface and you think, oh, look at how that's twisted, and wow, that must have, oh, hold on a second here, right? So we sat here and we twisted this thing. Note, let me get out of the line of sight. Note how that angle, that helical wrap, is at about 45 degrees. 45 degrees in real life, 90 degrees in Morse circle. So 90 degrees from the cross-sectional, right there, maximum tensile stress. Ductile metals will fail in shear, not in tension initially. And this thing failed in tension without a doubt with that little wrap. This thing, this material, even though it's steel and it's metal, is not ductile. This is actually a brittle material. Right now you go over to this one. This one failed right on the cross section itself. That means it failed right here on this plane. That point A was the cross-sectional plane, right? So that means it failed in shear, and ductile metals will fail in shear first. Now they may eventually get to a brittle plane, but they will fail in shear first. That's what creates the ductility. Tension is sort of breaking and rupturing those atomic bonds, whereas the shearing is actually taking the crystal and lattice structure of the metals and sliding them past each other, and that doesn't break the atomic bonds. That's why it creates this ductile kind of behavior. Now this little aluminum bar is very ductile compared to that other one, that steel one, that was ultimately a brittle material. It always gets me every time I look at it. I think it's ductile because I see this big long helical surface that's going on. All right, so what do you think? Piece of chalk, is it ductile or is it brittle? Now overall you say, well, I know it's brittle because everybody's broken chalk. Well, I don't know if anymore anybody has, but let's do the test. Let's try to rotate this in pure torsion without bending, which is actually a little tough, but we'll do it. Try it. Oh, did you hear that snap? And look at that helical wrap. This is chalk, is a brittle material, very weak in tension compared to its shear capabilities. Hence, that's why it fails like it does when you, in that helix, when you wrap it, because it's failing where you first reach that limit of the tensile capacity.